Welcome to this explainer. Today, we're uncovering a bit of a scandalous tech secret. If you've been around database design, you know the strict rules about keeping data perfectly organized. But today, we're looking at why the absolute best developers intentionally break those rules to build databases that look, well, badly organized. It's a fascinating strategic trade-off, so let's just dive right in.
Okay, let's dive into this, because this question really gets to the very heart of database architecture. You know the sacred golden rule among database purists, right? Full normalization. The rule is simple. You store every single fact exactly once. It guarantees strong data integrity. If a customer changes their name, you update it in one tiny little box, and bam, the whole system is perfectly correct. It's pristine, it's logical, and it's super safe. So why in the world would we ever abandon this beautiful perfection and intentionally introduce messy, repeated data? Well, I'll playfully tease you with the answer. Sometimes, sticking to absolute perfection will literally bring your entire system to a grinding, agonizing halt.
And that brings us to our core definition, denormalization. It's time to dramatically break that golden rule, because in the real world, denormalizing a database isn't an error. It's a highly controlled, deliberate trade-off. It is certainly not bad design by default. Think of it more like a calculated survival tactic to keep your read-heavy systems from completely crashing. By accepting some repeated, duplicated data, developers can drastically reduce the number of complex joins the database has to perform, and that massively speeds up how quickly data can be read and displayed to the user. You're basically trading a little bit of structural perfection for a whole lot of raw speed.
Now, what's really interesting about this slide is that we're essentially putting both of these designs on trial. On the left side, we've got the pristine safety of normalized design. It boasts way less data duplication and incredibly safe, easy updates. But the penalty? It needs way more complex joins to put a full picture together for the user. Then, on the right side, we have denormalized design. It boldly repeats data and makes updates much harder because a single change might need to be updated in 5 different places. But the massive payoff? Lightning-fast queries. It's a classic battle, prioritizing absolute correctness and maintainability versus prioritizing raw, practical speed for specific queries.
To really understand why we even make this trade-off, you kind of have to feel the pain of the problem. Imagine you're opening a critical dashboard, and you just watch a loading wheel spin and spin and spin. It's absolute agony. In a fully normalized system, just to show you one simple dashboard, the database might have to run repeated joins across incredibly massive tables, basically stitching together a million tiny facts on the fly every single time a user clicks refresh. All that heavy processing slows frequent read queries to an absolute crawl. It's this sheer need for speed that forces developers to step back and completely rethink their architecture.
And this brilliantly illustrates the solution. To solve that speed problem, developers use what's essentially an ultimate student cheat sheet. Think about it. Instead of running into a massive library and searching through 10 different books to find your answers every single time you're asked a question, you just copy all the facts you need onto one quick summary page. For a read-heavy application, we store summary values right next to the main record. For reporting and analytics, we pre-compute totals, so saving a daily sales summary instead of counting a million individual receipts every single morning. And for cache and common data, we just store things together to avoid those repeated joins. You just read the cheat sheet.
Let's look at some real-world, read-intensive examples where this cheat sheet method is absolutely mandatory. Think about an e-commerce product page showing the price, ratings, and seller names all at once, or an inventory screen showing current stock snapshots. But the most critical example here, a hospital patient dashboard. When a doctor opens a screen in an emergency, they instantly need the patient's name, their ward, their consultant, and a pre-calculated risk score. They absolutely cannot wait for a database to join 5 massive tables together. In this scenario, we just have to prioritize immediate reads over write efficiency. Speed here isn't a luxury, it is a literal necessity.
But, and you knew there was a but coming, we have to ask a pretty serious question here. What happens when the underlying facts change? I want you to really think about this for a second. If you rely on a cheat sheet that's copied information from all over the database, sure, that cheat sheet is incredibly fast to read. However, it is an absolute nightmare to update. Because suddenly you aren't just changing a fact in one master location anymore, you have to track down every single copy you made across your entire system. This is the heavy, heavy price we pay for speed.
Let's look specifically at the dangers of this approach, because the main disadvantages are pretty severe. First off, you have increased data redundancy, meaning you're eating up extra storage space. But far worse than that are the update anomalies and consistency problems. Imagine a customer updates their shipping address. In a perfectly normalized database, that transaction is simple and safe. But in a denormalized system, that address might update in the main transaction table while leaving a stale, completely incorrect value sitting in a copied dashboard summary somewhere else. Suddenly, the system has two different versions of the truth, and that is incredibly dangerous. So the crucial point is really captured perfectly right here. The reality of this trade-off is simple. Denormalized schemas simplify some queries, but they shift complexity right into data maintenance. You aren't actually eliminating the hard work, you're just moving it somewhere else. And this matters deeply because inconsistent data completely destroys user trust. Fast reads are incredibly valuable, sure, but if a manager pulls a lightning-fast report that has the wrong sales numbers, or a doctor sees a fast dashboard with a stale, outdated risk score, well, the system is completely useless.
Because of these massive risks, denormalization is never just sloppy or lazy programming. It is a highly calculated choice that requires serious engineering to balance the risk. To prevent users from seeing stale data, developers have to build extra maintenance logic. This means programming background refresh jobs that run overnight, or setting up complex database triggers that automatically force copies to update the exact second a master record changes, or maybe running large batch updates. You're basically buying speed on the front end by paying with complex maintenance engineering on the back end.
Let's move to and see how this spills into an actual methodology. Because the stakes are so high, architects use a strict 6-step evaluation framework. Whether you're facing an exam or leading an engineering team, you have to evaluate, number 1, is the workload read-heavy or write-heavy? 2, is there a proven bottleneck actually slowing down queries? 3, what is the exact scope of the fields that need copying? 4, what refresh method will keep those copies synchronized? 5, what is the risk if the data becomes temporarily stale? And finally 6, does this actually achieve simplicity for the user? Mastering this checklist is absolutely key to acing any evaluation of database design.
Ultimately, whether you're sitting in an exam hall or pitching in a corporate boardroom, your final judgment needs to be nuanced. A strong evaluation never says this technique is purely good or purely bad. Instead, the ultimate rule is this: denormalization is justified only when the speed gain is definitively worth the added maintenance cost. It is entirely about the specific context of the application. You're constantly weighing the need for blazing fast performance against the strict, unforgiving demands of data integrity.
Which leaves us with this final, incredibly difficult scenario. You are the architect. Your primary reporting dashboard is painfully, unacceptably slow and is frustrating all your users. But your core data absolutely must be perfectly accurate and consistent. When push comes to shove, which do you sacrifice? Do you sacrifice speed to maintain perfect integrity? Or do you sacrifice strict rules to give the users the performance they demand? It's the ultimate push and pull of database design. Thank you so much for joining me on this explainer. Keep asking those hard questions, and I'll see you next time.